following formulae in connection with the chapter friction will be discussed. This is the round off. This is the expression of pushing force applied on a body obliquely, and again we shall consider the expression of pulling force applied on a body obliquely. Then minimum pulling force applied on a body obliquely, that is F equal mu mg divided by cos theta mu sin theta. For minimum pulling force, dd theta of F will be 0, and finally we get the expression of minimum pulling force Fmin equal mg mu divided by root over mu square plus 1. And if we compare pulling force applied obliquely and minimum pulling force applied obliquely on a body, then we get the expression of F and Fmin. And if we consider the maximum length of hanging part of Hn, then the formula will be L equal mu divided by mu plus 1 into capital L. That is the maximum length of the hanging part of the chain. Then a body can be pressed against a vertical wall. In that case, the expression of applied force on the body will be Fx equal to mg divided by mu. That is the expression of applied external force. And if we consider the motion of insect in a spherical surface, then the insect will not slide down provided Fl equal mg and r equal mg cos theta. And finally we can prove that coefficient of friction mu will be equal to tan theta. Also, height attained by the insect when it travels from A to B is h equal r bracket open 1 minus cos theta. Now we shall discuss the individual formula discussed above. Formula set 2 in connection with the chapter friction. This is a rough surface. A body is placed on this rough surface and a pushing force F is acted on this body. F is the pushing force. F is the pushing force which is acted on the body at an angle theta with the horizontal. The pushing force F is applied on the body at an angle theta. This angle is theta. Now we can extend this pushing force F in forward direction in this way. The pushing force F is extended in forward direction. This is the direction in which the pushing force F is extended. We can draw the vertical line. This is a vertical line, and in this direction weight of the body mg acts vertically downwards. Mg is the weight which acts vertically downwards from its center of gravity. We can draw a perpendicular from this point on the horizontal line so that we can find the rectangular component of this pushing force. This component will be F cos theta. F cos theta is the rectangular component of pushing force F, and this angle will be again theta. Because it is a vertically opposite angle, we can draw another perpendicular on the vertical axis and we get another rectangular component of the pushing force F sin theta. In vertically upward direction, normal reaction R acts. R is the normal reaction acted on the body, and this is the direction towards right. This is the direction in which the body will be at the verge of moving under the action of the rectangular component of the pushing force F. That is, the body will be in the verge of moving under the action of the rectangular component F cos theta of the pushing force F. This is the direction in which the body is at the verge of moving, under the action of the rectangular component F cos theta of the pushing force F. And limiting friction Fl acts in the opposite direction to oppose the motion of the body. Fl is the limiting friction which comes into play when the body is at the verge of moving towards right, and limiting friction Fl acts towards left. Finally, we get the expression of the formula of pushing force F is mu mg divided by cos theta minus mu sin theta. This is the expression of pushing force F. F equal mu mg divided by cos theta minus mu cos theta, where mu mg divided by cos theta minus mu cos theta, where mu is the coefficient of static friction. Also, another formula of this pushing force is F equal mg sin theta L divided by cos theta minus theta plus theta L. Cos theta plus theta L. So this is the expression of pushing force applied on the body obliquely to move it. This is the expression of pushing force. Expression of pushing force applied obliquely on the body. Applied obliquely on a body to move it in. Pushing force applied obliquely on a body placed on a rough surface, rough horizontal surface, where theta L is the angle of friction and theta is the angle at which the pushing force F is acted on the body. And also here at equilibrium, because the body is at the verge of moving, so in equilibrium, F cos theta, the rectangular component, horizontal rectangular component F cos theta will be equal to FL, will be equal to the limiting friction FL, and F sin theta, the vertical component which acts downwards, F sin theta will be equal to R minus mg. F sin theta is the external force and R minus mg is the net internal force acting in the opposite direction. And we get F cos theta as R minus mg. From that we can prove that F equal to mu mg divided by cos theta minus mu sin theta. Number 2 formula. On this body, a pulling force F is acted at an angle theta with the horizontal. Weight of the body mg acts vertically downwards. Weight of the body mg acts vertically downwards. Now the pulling force is acted on the body at an angle theta. We can draw a perpendicular on the horizontal straight line. Theta is the angle with which the pulling force is applied on the body, and F cos theta is the horizontal rectangular component of this pulling force. And if we draw a perpendicular on the vertical direction, we get the rectangular component F sin theta in vertically upward direction, and R is the normal reaction which acts vertically upwards on the body. And this is the direction in which the body will be at the verge of moving. Direction in which the body is at the verge of moving. Now the limiting friction FL acts towards left on the surface in contact between the body and the rough surface. FL is the limiting friction which acts towards left, and the body will be at the verge of moving towards right. And the expression of pulling force is mu mg divided by cos theta plus mu sin theta. This is the expression of pulling force applied obliquely on a body at an angle theta placed on a rough surface. Also we can prove that F equal to mg into sin theta L divided by cos theta minus theta L, where theta L is the angle of friction and theta is the angle with which the pulling force is applied on the body with the horizontal. This is the expression of force or pulling force, expression of pulling force. Not only force, it should be pulling force. Pulling force applied obliquely at an angle theta on the body with the horizontal direction. Pulling force applied obliquely on a body to move it, placed on a rough surface, on a horizontal rough surface. And mu is the coefficient of friction of the rough surface with respect to the body. And also here at this equilibrium condition, in equilibrium or at equilibrium condition, F cos theta is equal to FL, where FL is the limiting friction. F cos theta is equal to FL, and F sin theta is the external force acting in vertically upward direction, that will be equal to mg minus r. F sin theta is the external force and mg minus r is the net internal force acting in the opposite direction. We get the expression of two rectangular components of the pulling force F, that is F cos theta is equal to FL and F sin theta is equal to mg minus r. and also mu is equal to tan theta L, where theta L is the angle of friction. Now we have to find the expression of minimum pulling force. Minimum pulling force applied on a body obliquely. Applied obliquely on a body. The expression of pulling force, general expression of pulling force, is mu mg divided by cos theta plus mu sin theta. We have another expression of force, and this is the expression of pulling force applied obliquely on the body. Pulling force, general expression of pulling force applied obliquely, not applied horizontally, applied obliquely on the body. And if this pulling force becomes maximum, pulling force becomes minimum, then dd theta of f will be 0, because if f is minimum, it will be constant. That's why differentiation of this pulling force with respect to the angle at which the pulling force is applied will be 0. And here dd theta of f will be 0. And from that we can prove that theta is equal to theta L, means angle with which the pulling force is applied with the horizontal on the body will be equal to angle of friction, where theta L is the angle of friction. Theta L is the angle of friction, and theta is the angle with which the pulling force is applied with the horizontal on the body. Also, F has another expression mg sin theta L divided by cos theta minus theta L. mg sin theta L divided by cos theta minus theta L. If the pulling force F is minimum, then theta equal to theta L, and F tends to F min. F min will be mg sin theta L, because in the denominator cos theta minus theta L will become cos 0 degree, which is 1. F min equal mg sin theta L. This is the expression of minimum pulling force applied obliquely on a body. And also now we know that mu is equal to tan theta L. So another expression of minimum pulling force is what? Mg mu divided by root over mu square plus 1. So this is the expression of minimum pulling force applied obliquely on a body at an angle theta to move the body. This is the expression of minimum pulling force. Minimum pulling force applied obliquely on the body, on a body placed on a horizontal rough surface to move it. Now we can compare pulling force applied obliquely and minimum pulling force applied obliquely. F is a pulling force which is acted at an angle theta with the horizontal, and on the right hand side again we can draw the same body placed on a horizontal rough surface. This is the pulling force, minimum pulling force F min, which is acted at an angle theta with the horizontal direction. mg, that is the weight of the body, mg acts vertically downwards. Mg is the weight of the body which acts vertically downwards on both the cases. Mg, that is weight of the body, acts vertically downwards. Now expression of pulling force applied on a body obliquely, that is F equal mg sin theta L divided by theta minus theta L. But the expression of minimum pulling force is mg sin theta L. And F has another expression mg mu divided by cos theta plus mu sin theta. But another expression of minimum pulling force is mg mu divided by root over mu square plus 1. This is the expression of pulling force, and on the right hand side this is the expression of minimum pulling force and it is obtained when theta is equal to theta L. Number 4 formula, a chain is placed at the edge of a table. Small m is the mass of the hanging portion of the chain. Small l is the length of the hanging portion of the chain. L minus L is the length of the portion which is at rest on the table, and m minus m into g is the weight of the remaining portion which is on the table, which acts vertically downwards, and R is the normal reaction acted on the remaining portion of the chain which is on the table. R is the normal reaction acted on the remaining portion of the chain which is on the table, and weight of the hanging portion of the chain, which is small mg, acts from the center of gravity of the hanging portion of the chain. Small m is the mass of the hanging portion of the chain, and here T be the tension acting on the remaining portion of the chain which is at rest on the table, and also there will be same amount of tension which acts vertically upwards acting on the hanging portion of the chain. T is the tension acting on the hanging portion of the chain, same amount of tension. And limiting friction Fl acts towards left to oppose the motion of the chain. Due to limiting friction acting on this portion, the chain does not slide. So in this case, tension T acting on the chain will be equal to limiting friction, and T is the tension acting on the chain. And this tension acts towards the fixed end of the chain, towards the edge of the table, where Fl is mu dot r, which is limiting friction, and mu is the coefficient of friction between the chain and the table. Fl equal mu into r, which is limiting friction. And we can prove that length of the hanging portion of the chain in terms of total length as L equal mu divided by mu plus 1 into capital L. This is the maximum length of hanging portion of the chain through the edge of a table. Small l equal mu divided by mu plus 1 into capital L, which is the maximum length of the hanging part of the chain, hanging part of a chain. L equal mu divided by mu plus 1 into capital L. Placed maximum length of the hanging part of a chain placed at the edge of a table, placed at the edge of the table. Small l is the length of the hanging part of the chain, hanging part of the chain, and L minus L is the length of the remaining part of the chain which is at rest on the table, length of the remaining part of the chain which is at the rest. Number 5 formula, a body is placed against a vertical wall. This is a body or slab which is placed against a vertical wall, and its weight mg acts vertically downwards from the center of gravity, and external force Fex is acted on this body perpendicular to the wall. This external force Fex acts, and as a normal reaction R acts towards left, and external force Fex is acted on the body towards right against the wall, and this is the direction in which the body will be at the verge of sliding against the wall. Direction in which the slab or the body is at the verge of sliding or moving against the wall, verge of sliding against the wall, and this is the wall, vertical wall. And this body will not slide if limiting friction Fl acts vertically upward direction in this way. This is the direction of limiting friction, and Fl is the limiting friction. At equilibrium, that means the body will not slide down. At equilibrium, the body will not slide down against the wall, will not slide down if limiting friction Fl is equal to mg, and also normal reaction R is equal to Fex. Again, limiting friction Fl is equal to mu dot R, where mu is the coefficient of friction between the body and the wall. So finally we get the expression of Fex as Fex is equal to mg divided by mu. This is the expression of external force Fex which is acted on a body. We get the expression of Fl as equal mg and R is equal Fex. And Fex, that is the applied external force on the body to hold it against the wall. Fl is the limiting friction. Fl is the limiting friction and R is the normal reaction. R is the normal reaction. And Fex is the external force, applied external force on the body against the wall. And number 6 formula, an insect moves from the point A to B, and we can draw the radius of this circular surface or spherical surface, and we can draw two radii. This are the radii of this spherical surface. B is the final position of the insect, and we can draw the weight of the insect mg acts vertically downwards from the point B. When the insect reaches at the point B, weight of the insect acts downwards, and theta is the angle between the two radii, and O is the center of this imaginary of this spherical surface. And we can resolve mg. We get the rectangular component mg cos theta, which acts radially outwards, and this angle is also theta. Mg cos theta acts at an angle theta with mg, and we can draw another side of a rectangle of the rectangle taking mg as diagonal, and this side of this rectangle is the another rectangular component of the weight mg, and this side denoted by green color is the another rectangular component of the weight, which is mg sin theta. And at the final point B, the insect will not slide down provided limiting friction Fl acts tangentially in this direction. This is the direction, and Fl acts in this direction, and if Fl is equal to mg sin theta, the insect will not slide down from the point B, and radially inwards normal reaction R will be acting. R is the normal reaction acted on the insect applied by the spherical surface, and small r is the radius of the spherical surface. And we can draw another radius of the spherical. We can draw a normal from the point B on the radius OA, and this normal is Bn. This normal is Bn. So this is another radius of this spherical surface R, and we can draw the height attained by the insect. When the insect moves from A to B, height attained by the insect will be small h. Initially, the insect was at the point A, and it travels from A to B along this spherical surface, and it reaches to the point B. The insect travels from A to B, and B is the final position of the insect. Final position of the insect. The insect will not slide down, and remains stationary at the point B on this spherical surface if Fl is equal mg sin theta. That means limiting friction Fl will be equal to the rectangular component mg sin theta. Fl will be equal to mg sin theta. Also, Normal reaction R will be equal to mg cos theta. R will be equal to mg cos theta. Normal reaction R, capital R. R is the normal reaction acted on the insect applied by the spherical surface. And Fl is the limiting friction. Fl is the limiting friction. Also, limiting friction Fl is equal to mu dot R, and we can prove that mu equal to tan theta. Mu is the coefficient of friction between the insect and the spherical surface, and theta is the angle subtended by the final radius at the point B with the initial radius R at the point A. Also, we can write down the expression of height attained by the insect. When the insect travels from A to B, height attained by the insect is h, or change in height will be h, which will be equal to an. Insect travels from A to B, and change in height will be vertical height will be an. That is h equal an. Finally we get h equal r1 minus cos theta. So h equal r1 minus cos theta. So this is the height up to which the insect crawls. Again, mu is equal tan theta, that is coefficient of friction mu equal tan theta, and therefore h equal r bracket open 1 minus 1 divided by root over mu square plus 1. That is the height up to which the insect can reach.